Let's study collusion. There are two types of collusion, elastic, inelastic. In both collusions, momentum is conserved. So the momentum before collusions and after collusions are equal. Later we'll show you the proof. In the case of elastic collusions, not only is momentum conserved, you will also have Ke being conserved. In the case of inelastic collusions, you can further rationalize them into two types. One is completely inelastic, whereby it means that the colliding bodies actually join together as a single body thereafter. And the other will be that it's not completely inelastic, which means the particles do not coalesce. Let's take a look at why momentum is conserved for all types of collusions. So when a body A collides with body B, the force exerted by A on B is in this direction. It's in the direction indicated, while the force exerted by B on A is in the opposite direction, but they are equal. So in terms of vectors, FAB is equal to negative FBA. Given that the interaction between the two bodies occurs over the same duration, we could actually integrate each of them, dt, and as you can see down here, it will remind you of the formula of your impulse. So it means that the change of momentum of your body A is equal to the negative of change of momentum of your body B. So by rearranging them mathematically, you will find that the momentum of the body before collusions is equal to the total momentum of the bodies after collusion. So the momentum of a system is conserved. Typically, we call this the conservation of momentum, and hence in short acronym COM. In the case of elastic collusion, you will find that aside from the fact that momentum is conserved, the kinetic energy is also conserved. So we typically use the acronym in short form COE. So with these two equations and two unknowns, V2 and V1, which is respectively the velocity of the bodies after collusion, we can use these two equations to solve them simultaneously and obtain V1 and V2. Alternatively, for elastic collusion, we could solve V1 and V2 without using conservation of energy. We could just use the conservation of momentum and the relative speed method, which is that relative speed of approach is equal to the relative speed of separation, which is what you see in this equation here. So let us now mathematically show you how we arrive that the relative speed of approach is equal to the relative speed of separation. We still start off with the conservation of momentum and the conservation of kinetic energy. By actually doing mathematical manipulation from equation 2 and using the fact that x squared minus y squared is equal to x plus y multiplied by x minus y. Using that, we are able to apply and we are able to mathematically alter the expression to as such. And from there, you can see that we could actually divide equation 3 by equation 4. And that's how we arrive at the relative speed method. This is actually a faster method for solving equations. We'll now use an example to illustrate how we can solve the questions. Let's now take a look at the example as to how we apply the conservation of momentum and relative speed method to an elastic collusion. Say, for example, we have a mass M1 and M2, all right? M2 is 2 kg, M1 is 1 kg. Initial speed is as such, they're moving towards each other. And after that, they collide. We are tasked to find out what is the final velocity after the collusion. The first step to do is to state the convention. So for this example, we are saying that the left to right is actually positive. So in this case, I will straight away assume that the final velocity of V1 is as such and V2 as such. Okay? So bear in mind that the whatever convention that you state, you should always have it the same. All right? So based on this assumption that we make, that these are the final velocity after the collusion, we can first apply COM and actually do the mathematical calculation, which in this case, you can see, we should sum up all the momentum, all right? You sum all the momentum before collision and all the momentum after collision. So in the momentum for M2, U2, because the direction is in opposite to the convention, it will be 2 times 1.5, that will be -3. Okay, so it might be better for me to do that. So that will be -3. So therefore, because of that, it's -2. So it's V1 and then plus 2V2. So we're assuming both of them are in the positive direction. Next, when we apply the relative speed method, the speed of approach is in this direction. So the speed of approach will actually be, you will subtract with U2, all right? And be mindful that in this case, your U2 must in actual fact be a negative number because it's they are in the opposite direction relative to the convention. So based on these two equations, if you add the both of them together, the minus V1 and the V1 cancel away to give you 3V2, and minus half plus 2.5 gives you half. Bear in mind that when we calculate the momentum from U1 minus U2, you have to take note that U2 had to be negative 1.5 because it's pointing in the opposite direction to the convention. And basically solving that, you'll get a V2 and V1 as such. And take note that your V1 is in actual fact negative. So what happens is that after the collision, the ball in actual fact move this way, move in opposite direction. So sometimes for students, what they do, they rationalize the momentum of each body, and then they concluded that the momentum of this body is larger than this body. So therefore, the net momentum should be in this direction. Hence, because of this, either one of the body need to move its momentum in this direction, or both the bodies to move in that direction. In this case, say for example, we decided to change the direction of V1. Instead of going from right to left as positive, we make it go from right to left. In this case, in our calculations, we have to remember to put a negative here, because now the final momentum of your M1 body is actually in the opposite direction to the convention. So this will end up as minus V1. In the second equation, it is important that one need to realize that if this value is pointing in both this direction, then what they do is that they no longer subtract, they should be just adding. So with these two equations, by adding the first and the second equation together, we still end up as 3V2, as you can see, as half, and your V2 is still 0.17, but your V1 that you have calculated will now end up as positive 2.31. Hence, in summary, what we advocate in exam is to stick to the convention, meaning to say you just let V1 and V2 point in the direction of the positive value. And then the maths will work out itself. If it is pointing in the opposite direction, then they will turn out to be negative. If you are exercising some form of judgment, then it becomes pivotal that you ensure that you put the negative signs as we illustrate here, or otherwise in this case, this has to be a positive sign. So the common mistake that students make is that they didn't flip the sign to V2 plus V1, okay, as the relative speed of separation. And because of that, mathematically, the answer will be wrong.